Brett is an associate professor in agriculture and biosystems engineering at Iowa State. He leads an integrated research and extension program focused on ventilation design and management, climate physiology, mass mortality management, and several other topics related to the swine facility. His mission is to provide and advance the science and technology needed to address aforementioned areas in swine production systems. His program aims to generate practical solutions to current and emerging issues surrounding animal agriculture and its producers. Please help me welcome Brett Ramirez to the stage.
All right, you want the bad news first? This is an hour-long conversation, so hopefully nobody has anywhere to be this afternoon.
Spoken like a true professor.
Yeah, we're going to go for a whole hour. If you want the Cliff Notes version so you can get up and leave right now, manure temperature is not constant throughout the course of a year in a deep pit barn. So if you want the... I'll get into a little more detail, but that's the Cliff Notes version. But before I get started, so this is the work of my master's student, Wyatt Kendall, and then couldn't be done possible without the help of Drs. Heinrich Chung and Dan Anderson that helped immensely to get this study done. So I'm going to go through a bunch of different things related to what we did in monitoring temperature in a deep pit barn, and then also get into talking about some of the methane measurements and what the impact that has on methane generation. So why do we care about this? Really, this was driven from two standpoints. One is, are we accurately quantifying how much methane and what our carbon footprint is from these barns? Then also, for the anaerobic digestion piece, what is the temperature of this manure that could be being fed into these digesters, and is that something we need to be thinking about? So the overall goal was kind of based on that sustainability story, making it better. We know that methane has a 28 times higher global warming potential than carbon dioxide. Manure does account for a large fraction of those total emissions, and we know that methane is generated from that breakdown of that manure. It gets released, then it's either emitted from the barn, or it could be used as a fuel from a anaerobic digester. So there's a lot of things that affect methane productions. A lot on the microbial side, but there's also, when you're plugging it into one of those calculators, a lot of it has to do with temperature. And that temperature has a large impact on how much methane is being produced. So if you're using the IPPC guide, that's the chart up there on the left if you take it out of the table. And that shows you what your methane conversion factor is based on your manure temperature. So I'll get into, we compared just using a constant temperature, which I believe when I started this, I thought it would probably be pretty constant throughout the year. Told my grad student, you're either going to have some interesting graphs, or it's probably going to be the most boring graph and be a straight line across the page, and that's it. Luckily, it doesn't look like that, and this turned out to be a lot more interesting than I thought it would. So as that manure warms up, it's going to generate more methane. Warmer manure, more methane, higher carbon impact. Obviously, again, manure storage, time, pump out, surrounding things, all these things are going to go into what affects that deep pit storage temperature. So really, we wanted to know, what is the temperature inside the barn? I think between Dan and I, somebody is always asking us, what is that temperature throughout the year? Dan kind of had an idea, but he typically just assumes a constant temperature. He had previously only measured in pump outs, and we'll get into the answer to that question. Does just measuring monthly in a pump out accurately represent what the actual entire pit is doing? So on the temperature side, we wanted to look at trends in the pit. Do we actually have differences vertically and horizontally across the pit? We looked at two different barn types. Is that going to have an impact? How many sensors do you actually need to monitor manure temperature? Can you get away with just one? How frequently? And then using it across Iowa and what that might look like for deep pit barns across the state. Then looking at the methane portion, we actually took manure samples, calculated the methane production rate, fed that back in and compared it using temperature data. Then we also used a laser to do methane concentration inside the barn, compared that to what we measured from the manure samples, and then try to figure out what this all looks like. So at first, I'll start off with the monitoring temperature and the analysis in our deep pit barns. So we picked two commercial wean to finish barns. They're probably within about an hour northwest-ish of here. Took took us a little bit of time to find these exact ones because we didn't want any surrounding tree cover. They had to be deep pits, similar flows, mechanical ventilation, again, similar on that growing cycle, so we just didn't get anything widely different across the barns. So the big difference between barn A and barn B was barn A had no pit ventilation, and it was a single wide, and barn B did have pit ventilation, and that was a double wide barn. So single pit versus a pit with a pit partition. So with barn A, this is the layout. So we end up measuring air temperature and relative humidity inside the room. That would be those orange circles. We then use those blue diamonds where are going to be each of our temperature sensor arrays that went down into the pit. We also stuck 2 soil temperature sensors outside the middle of the barn. Those would be those green boxes in the middle to the right. Those were at 2 different depths because we'll eventually relate pit temperature to manure temperature, or soil temperature to pit temperature. Measured temperature in the pump out. We also used a distance sensor in the pump out to monitor how much manure accumulation we had. And that was about it. So this is on barn A. So then we stuck 2 temperature sensors across the barn because we assumed symmetry down the middle. So instead of over instrumentation, obviously there's cost and labor limitations to doing this. So we stuck just 2 over there because it was quick, easy. Want to make sure it at least matches and that symmetry assumption holds true. So barn B was a double wide. Same shapes represent the same things. It's very similar setup, but this one again has a pit partition with annexes in it. And so we did the same thing of measuring depth, soil temperature, pit temperature, and then also again just to verify is one side of the deep pit with the partition different than the other side of the deep pit. So what this looked like, so we use a completely wireless temperature sensor network. So we measured at 3 depths, and essentially, if you see where the manure line is on that diagram, is that because the manure never reached temperature sensor 3 there up at the top? I could say you can blame the advisor for picking that distance. It was just a little too tall, and we just never got manure up that high. So those are all measured from the bottom, so that was a little bit of oversight, so it's kind of a waste, but at least now I have really good data on what headspace temperatures are for whatever that's worth. But that's at least there. So they were suspended with a weight on a steel cable, and then you can see in the picture a piece of steel conduit basically protected those wires from the pigs destroying it. And then it went up to a gateway, and then all the data was collected, stored on the cloud, accessed, and downloaded. The bottom left there shows the 2 soil temperature sensors that we jammed in the ground outside. For the most part, this setup worked pretty good. We had a pretty low failure rate. The only times we had issues is when the gate wasn't right on the slat gap, and we'd get some rubbing between the conduit and the wire in the slat. That would eventually sever it, and then we'd have to replace it, but that only happened a handful of times. And amazingly, those pipes never came off. So it takes about 6 or 7 U-bolts on a gate rod to keep a pipe up. So this is comparing one side of the pit to the other side of the pit. For the most part, they were pretty much always equal, so the symmetry analysis pretty much held true. The only thing that it didn't hold true was in that barn B, and the only thing we can figure out is why it took a couple weeks for that other half of the pit to come up to the temperature is maybe the pump, the annexes between pits was clogged, and maybe manure got to an uneven level and it just wasn't being transferred and equalizing out correctly. But once after those few weeks passed, pretty much both sides are about the same temperature, and so that symmetry analysis held true. So here's what the manure temperature looks like across the course of approximately about 11 months. So the black line there is our manure depth, and then the color scale is the change in manure temperature over time. So we sampled at a rate of about 1 hour for all the temp sensors, so it's pretty high resolution. And so that manure temperature, you can see, obviously it's warm during our summer months here in the upper Midwest, cools off in wintertime, and kind of changes a little bit throughout the year. And so the range is around, low 60s up until the, mid to low 70s throughout the course of the year. And so you can see on that second temperature sensor that was the one a little higher up, it was definitely a little bit warmer than the other sensor, and that's about all the data we were able to capture when that sensor was actually submerged. So here's the comparison between the outdoor temperature in blue, the manure temperature in orange, and the soil temperature in yellow. You can kind of see, obviously they're going to kind of all trend together. But that manure temperature is insulated to some extent and doesn't quite change as much as that soil temperature or outdoor temperature. But it does fluctuate throughout the year and warms up and cools off based on the different seasons. So then we did an equivalence test. So this is going to be figuring out at what point does our two temperature sensors become equal, and how far down in the manure would one have to measure before you could assume that at the two different depths they were essentially at the same temperature. And so our threshold was 3.6 Fahrenheit or 2 Celsius to determine that they were equivalent temperatures. So what we had to do is basically go every 2 centimeters or just about an inch in accumulating manure, run this equivalence test to determine if they were all the same, and then incrementally go through it over time to figure out at what point this happened. So essentially for both barns, the top 10 inches of manure was not symmetrical with the rest of the manure in the pit. So you can assume it has direct contact with the barn air, which is presumably always going to be warmer than the manure temperature. Plus you always have fresh urine and feces being deposited on that top layer, which is going to be at the body temperature of the pig or close to it. So at least that top 10 inches always tended to be warmer than the rest of the manure, and that's how, if you are taking a manure temperature sensor, you need to make sure it's at least below the 10-inch level of the top surface of the manure. So then across the 6 different locations of the barn, we were trying to see, is there any difference in the horizontal difference in temperature? Essentially, the answer is no. They are all basically the same, and our absolute differences were, 0.1 C, which is, 0.2 of a degree Fahrenheit. So essentially, across the pit, horizontally speaking, manure is pretty much the same temperature. So that graph there shows the average temperature difference across the horizontal plane, and the maximum there being, no more than 1.82 degrees Fahrenheit at any given time. So all within the measurement accuracy of the temp sensors. So then the next question was, if you do just measure in the pump out, just because it's a little bit easier to access, just easier to put things in, you don't have to worry about pigs. So is the pump out temperature the same as the rest of the pit, right? So the pump out has a much smaller surface area that's exposed to the soil and can be more easily influenced by the dynamics of what goes around outside the barn. And so the dashed line there is our pump out, and the solid line there for both the barns is the rest of the sensors in the pit. So for the most part, again, it follows what the pit does. Where you see the biggest differences between the pump out temperature and the rest of the pit temperature is in the, I believe it's the colder months. Yep, and it gets similar in summer. In the cold, more influenced by the soil temperature, which stays constant, versus in the summer where everything just warms up and it gets closer in temperature. So then what we did is decide what is the difference in the lag time between getting the pump out temperature and the pit temperature to come together. So doing a little math, barn A lags behind from the pump out to the pit for 10 days, barn B is 2 days. We attributed that difference to mainly the one barn had just about 1.5 foot more manure than the other barn, just so it took longer to respond over the course of that period. Then fit a line. So the goal here was using some of Dan's data, was to then go back and figure out across the entire state of Iowa, because he sampled a ton of barns from 2012 to 2013, every single month in the pump out only, so he didn't actually have pit data, and he never knew really what is that difference. So created this little regression to be able to use our data and information to then apply it to his data across. So because they're so similar, this is basically the results of all of his samples, again, just showing across the entire state of Iowa, because he did it from every single corner. It does show that pit temperature does change throughout the year, and it is not simply just a constant temperature that's somewhat equivalent to the soil temperature. All right, so now transitioning into the methane data. This is the laser we use. We worked with the USDA ARS here in Ames to help get this done. So we set that laser up, and my slide got out of order, so just bear with me. But basically, this laser shines the laser down the length of the barn, and it picks up the average methane concentration for that room within the path of that laser. So monthly manure samples were taken. This is basically the equations he used. Basically take that sample, divvy it up, and then run it through a gas analyzer, incubate it, and then you're able to calculate what that methane production rate is coming off of that particular manure sample. So here's what we ended up getting for our calculated that monthly methane generation rate. So you can see both the barns were kind of different, which is not uncommon just because that microbial differences between the different pits can lead to just widely different methane production rates. So it kind of didn't really have many trends, but there's kind of what we came up with our methane production rates. They were basically looking at from what Dan did across hundreds, like it was 50, 60 some odd barns. We're within reason. The one barn's a little on the low end, but it's still within reason of what you could expect for methane production rates from a deep pit Iowa swine barn. And then if you want to break it down per pig space, just to kind of normalize it, because we had two different size barns with different inventories. Again, you just see, nothing really interesting or can really be explained other than the microbial community differences in each of the pits. So then if we compare our measured methane production rates from the laboratory to using equations based on temperature, if you assume a constant temperature throughout the year, it ends up with an average difference of about 21% from our measured to predicted using temperature. Based on a monthly measurement of just temperature, so if you just sample our data only at a month, you get down to about a 5% difference. And then if you use a linear interpretation between the months of temperature, you can get down to 3% difference in between the measured production rates and what you would estimate using temperature. So then with the uncertainty, the biggest basically showing anywhere from 5 to about 15-20% of uncertainty in that actual methane production rate. The biggest uncertainty wasn't really in the temperature measurements. They're pretty accurate. It mostly came down to the repeated samples of the manure itself. So if you ran the test sampling the methane being produced in the lab on 3 samples, he would get pretty different results, and that's where most of this uncertainty comes from. So switching back to the laser, so if you take what you need to estimate methane emissions from a barn, you need your ventilation rate and you need your concentration. Then you can do some math to figure out what your emission rate is. So instead of going through and measuring each fan's ventilation rate, just because that's very time consuming, we just monitored carbon dioxide, did some math, made some assumptions so we could figure out within reason what the ventilation rate of that barn is on a continual basis. So assuming how many pigs you have, concentrations going in, going out, assume a heat production for the pigs and how much CO2 they produce, you can figure out what your ventilation rate is. So here was our average methane concentrations over the course of a month. We only did 1 month just because that's all we had time to do, and it was in between some barn maintenance and some flow changes, so we were only able to get a month before we had to get the system out. But concentrations were anywhere between 45, 50, and upwards of 75 parts per million, so pretty low in the grand scheme of things if you're thinking about it from a LEL value. And so when we take our laboratory experiments and are measured with the laser, it was only about 1.6 kilograms over the course of that month, or only about 10% difference. So luckily the two compared, so that makes sense from doing it from a emission standpoint, and then also using the lab standpoint. Relatively low uncertainty within the reason. And the big issue there is just trying to calculate ventilation rate using CO2, just because it has inherent assumptions that are pretty hard to evaluate. So conclusion, Temperature varied substantially over time. It really shouldn't be treated as constant. There's probably some different ways we can use like a soil temperature if you have that at least, or even outdoor temperature. You can probably get to what manure temperature might be, because some of those swings are pretty large, and making low frequency, so probably once or twice a year is not going to be sufficient enough. You might have to be at least doing it monthly to get that representative value of what that deep pit temperature would be. You can use one sensor. You don't need to measure in different depths as long as it's sufficiently beneath the manure surface, and you don't need to measure horizontally either, just because that one sensor in one location should cover the rest. The temperature of the pit itself is pretty uniform. They both had pretty different methane production rates. Again, it's hard to tell because all pits are different. They all have different microbial communities. It was relatively consistent in the barn over time, and kind of validated both our laboratory techniques and our in-barn measurements that we were getting somewhat of a reasonable number that makes our, increases our confidence if we want to extrapolate this out across Iowa to figure out what methane production might look like throughout the state. So with that, I will take any questions. And I got us done before 4:30.
Questions for Brett?
And also, if you want more information, his thesis is online. So if you go on the digital repository, you can find his thesis and get all the exact same information that I just had today. Yes, John.
Yeah, thank you for the presentation, Dr. Ramirez. Have you done a similar study or anyone else in shallow pits? And if not, would you be able to start in Oklahoma next week?
Yep, I'll be down there. I'll leave this weekend. Now, to my knowledge, this is the first time anybody's done this just in general. I really wanted to throw it in a lagoon up here just because that hasn't been done. So this is, to my knowledge, the first data that anybody's ever collected on long-term, or at least in the public domain, of what temperature is in a pit. Like even the information from Dr. Anderson, he never published it. So he had to pull up a spreadsheet and send it to us. So not to my knowledge.
And as before, thank you for your presentation, the information. What I'm curious about, and it may be extraneous to the line of research, was the nutritional status of the pig's diet or whatever. I'm looking for the carbon-nitrogen balance of the manure, just out of curiosity.
That was outside the scope of what we did, but the USDA is currently working on that at the moment and doing a very detailed look into that. So I think if you hang tight for about 2 more years, they'll have a lot better information on that relation between nutrition, growth, manure, and emissions.
Any more questions? If not, that wraps up our program for today. Let's thank our speaker.